So we are going to start with hypothesis testing with 2 samples. That's as I mentioned, a very important topic. So with hypothesis test with 1 sample, we were choosing 1 sample, we were making a claim, and then we were either supporting or not supporting the claim. So, so we went through the process of building the hypothesis, finding the standardized test statistic, then finding the, well, compare this test statistic with the alpha, either comparing the p-value with the alpha or comparing the test statistics with the critical value. So in the critical value approach, remember, we find the critical value that separates the rejection from the no rejection area. And then if my test statistics falls within the rejection region, we reject, otherwise we fail to reject. So these 2 methods are very important. Let me mute everybody. So so now is a little bit different, because rather than making a claim and saying this is right or wrong, or I don't have enough information to support this data, what we are going to do is we are going to compare 2 different samples. So let's say I am not interested. Well, so let's say that the president of Lehman says that girls are smarter than boys. So so what do I do to prove that claim? Well, in this case, I'm gonna find a group of men, a group of women. I'm gonna look at their GPAs, and then I'm gonna compare the means. And based on these means, I'm gonna say whether or not the statement is correct, or the statement can be supported by this statistical significance. So so we are going to be using 2 different samples to make comparisons, and then we are going to come up with a so we are going to come up with a decision whether or not we support that claim. So that's a very interesting case, because we can have 2 different samples and see whether or not they are in this case, if the means are different, or the standard deviation, or the variance, or the population proportion, so that they are significantly different from each other. So today, so once again, we are going to do a hypothesis testing with 2 samples. So what we are going to do is, well, what we have in reality is that samples can have 2 different, can be of 2 different times. So we are going to use these 2 sample hypothesis tests to compare 2 parameters from 2 different populations. And as I mentioned before, we have 2 different sampling methods. So whether the samples are independent or the samples are dependent. So independent samples, the sample selected from one population is not related to the sample selected in the second population. For example, you have 2 independent samples. When you have a group of men and a group of women, so so a man cannot be a woman and vice versa. Well, in this case, we're assuming that. So these 2 samples are independent. So one element of one group cannot be part of the other group. So we also have these dependent samples. So the dependent samples are also called paired or matched samples. So each member of one sample corresponds to a member of the other sample. For example, I want to see how much of a good teacher I am, right? So I'm gonna give you a test at the beginning of the semester, and then I'm gonna give you a test at the end of the semester. So I'm gonna compare the pre and the post. So that's gonna be important for me, because I'm gonna be making assumptions that I am teaching this statistics class to help people to understand statistics. So I want to see how many people are improving their grades. So so the dependent samples, of course, I'm going to use my students at the beginning of the semester. I'm going to use my students at the end of the semester. So those who are in the pre, they are going to be part also of the post testing, right? So that happens very often. So this kind of sampling is very important. In many cases, we can use, well, this kind of sampling methods are used many times in pharmaceutical studies. For example, you want to test how Lipitor improves cholesterol. So you find an independent group of men, an independent group of women, or you find an independent group of Hispanics, an independent group of whites, or whites and blacks. So you can find different groups, or you can take subjects that you are measuring those data from the same person, the pre and the post, right? So pharmaceutical companies use this very often. In many cases, surveys that have to do with quality improvement might use these kind of samples that are independent or dependent. So we have plenty of examples. So this is something that many researchers use to determine whether or not the two different numbers are equal from each other, right? So or they are different from each other. So in the case of the mean, just imagine that you have a mean for a GPA. So just imagine that you have a GPA that is going to be measured um, in points. So the 0.40, so it's going to be the highest number of, so let me make it bigger. So you have a 4.0 that is measured in the GPA format from 1 to 4, or from 0 to 4, or you have one that falls in the scale of 10, right? So this is the average, right? So or this is something that many schools use. So at some point, I might have a mean in one school of 3.7, and then a mean of the regular score that is 8.75, right? So I want to know how these averages are different from each other, or they might be the same, right? So I don't know. So that's what we're gonna do. We are gonna have two different groups in some cases where the numbers are different, and we want to make sure that those numbers are reflecting or they are not significantly different from one another, okay? So that's what we can do, and that's what we're gonna do with this hypothesis test. So we are gonna find two different means, and then we are gonna compare them and determine whether or not they are different, statistically different. So before I continue, I want to say that all the materials, if you are now here, so all the materials for this class, for today's class, we have the PowerPoint and we have the Excel assignment. So you can download the Excel assignment. We're gonna use it today. So, so please do so. Go to Blackboard, go to module number 5, and find these PowerPoints and the Excel file inside chapter number 10. So once again, we have these two samples. One can be independent, one can be dependent. This is the idea. We have a sample that is independent. Those that belong to sample 1 are not the same than those who are in sample 2. As we can see, the sample size can or cannot be different. So in this case, we have 4 elements. In this case, we have 7 elements, right? So in many cases, we might have samples that are independent, that have the same number of individuals or components, or samples that can have some different components, but it doesn't matter. The idea is that those who are in sample 1 are not part of sample 2 and vice versa. So those are independent samples. We have the dependent samples. Those who are part of sample 1 are going to be part of sample 2. So in this case, all the elements have to be the same, right? So we have 2 examples, example independent and dependent samples. Classify the pair of sample. Of course, you have the answer right here, but just let's pretend that we don't know. So classify the pair of samples as independent or dependent. So weights of 65 college students before their freshman years begins, and then the weight of the same 65 college students after the freshman year began. So, of course, we are measuring the weights of students from before and after. So basically, that is going to be a dependent sample. So the samples can be paired with respect to each student. So in this case, we can see that we have the before and the after. So that's very important because so we can see that elements in sample 1 are going to be exactly the same as element in sample 2. So in many cases, when you keep doing this over and over, so when you keep doing this over and over, in many cases, these type of studies are called longitudinal studies. So, for example, Lipitor wants to know how effective the drug is going to be. They do the pre, the post, and probably some more testing over time. So they are testing one individual over time, and of course, they have many individuals over time. So the simplest case is this dependent sample when we have the pre and the post. But as I said before, that can evolve to something that is called longitudinal studies. So also we have the second case. So classify the pair of samples as independent or dependent. So we have the scores of 38 adults male on a psychological screen test for attention deficit hyperactivity disorder. We have 50 female people, adults, on the same screen testing. So that is basically an independent sample, right? So we have 38 adults, we have 38 males, 50 females. So they are different groups. Of course, we are assuming that males cannot be in the group of females and vice versa. So if you are doing a study, in many cases, of course, you have to be very clear about these kind of things nowadays with different identifications. But so in this case, it's very clear we have male versus females. So we can do this kind of different sampling to see, for example, who is more likely to suffer attention deficit disorders, and that might be the goal of this student, of this study, right? So we have male, females, and we want to know who is more likely to suffer this. So we can have a group of blacks and whites, or Hispanics and whites, and compare race, ethnicity. So we know that many of the biological differences between men and women make things very specific. So before I continue, I just want to bring this to your attention, guys. I was talking to people in my department, and I said, well, I'm recording these sessions, and I am posting them in Blackboard, and I do it through YouTube because it's very easy for me. So they were bringing that to my attention, that I need to ask permission to you guys to, because your names are there. So if you don't feel comfortable having your names there on the screen, please send me an email. I will erase all these lectures right after the semester. I will download, sorry, I will erase all these lecture after the semester, but I think in the meantime, we need it. So if you don't feel comfortable having your, I mean, I don't know who's gonna watch these lectures besides you. But if you have any issue, please let me know. I just want to bring this to your attention because the department said that I need to ask permission to students to post these lectures online. And I don't know how, well, I just want to say that, okay? So you have any issue, please let me know. So once again, we have two different samples. We have the, so I read Terry's email. I'm gonna send you the file in a few more minutes. Just give me 1 second, Terry. So once again, I was kind of distracted. We have independent and dependent samples. We have two examples of these. So we're gonna do the hypothesis test, very similar to the one that we did before. So we have two sample hypothesis test with independent samples. So we are gonna look at the first case. We have two samples. We know that the samples are independent. So the elements on group A are different from elements in group B. So so we know that we have two different hypotheses, the null hypothesis and the alternative hypothesis. And we know the signs and the symbols that they are gonna be given. So if we have the null hypothesis, we have these symbols. If we have an alternative, we have the counter argument. So so remember, we already went through this. So the alternative, so once again, is gonna be the hypothesis that we want to prove or disprove, because that's gonna help us to support or not to support the claim. So so once again, we have the null and the alternative. The alternative is gonna tell me the type of test, and the null hypothesis is gonna tell me whether or not I am gonna support or I'm gonna fail I'm gonna reject or fail to reject the null hypothesis, and therefore the claim. So so that is something that we did before. So we have the null hypothesis. In this case, it's gonna be a little bit different because, for example, we have a null hypothesis and an alternative hypothesis, right? So in this case, for example, if mu is the parameter that I want to analyze, but I have two different mu's, so it's gonna be mu1 and mu2. So I'm gonna hypothesize that the difference in the two populations are either equal. So if we are using this, and therefore the two different groups are gonna be unequal, right? Or we can use any of these symbols, right? If I say less than, this is greater or equal to, greater than or equal to, and all these kind of combinations. So the point is that in the previous, we were comparing my parameter with a constant. So I was saying mu is equal to 25, right? So in this case, this is for one sample. So because we have two samples, now we are going to use the parameter to compare the two different populations, the two different population parameters, right? So this is two samples, this is one sample. So we were comparing one sample with a constant, and here we are comparing how the two samples can be equal or not equal, right? So keep that in mind because it's very important. So remember, we have been seeing these cases with the mu, with the variance and the standard deviation and the population proportions. So so this is hypothesis test. So we have to translate the verbal statement on the as a mathematical identity, and then we are going to be able to do our work. So in this case, as I mentioned, so we have a comparison of the two different parameters. In this case is mu. So mu can be equal, and then the counter argument is going to be not equal to. So that is a two-tail test. We know that. So then we have the greater than. The counter argument is going to be less than or equal to. So the two population parameters, one, the mu1 is going to be greater than. So we have a right tail test. And when we have the mu less than mu2, and mu1 is less than mu2, so the counter argument is greater than or equal to mu1. So in this case, we have a left tail test. So regardless of which hypothesis you use, you always assume that there is no difference between the population means. So in this case, it's more clear because the hypothesized difference in these two different parameters is going to be 0. So that's what I want to prove. I want to tell so I want to withdraw 2 samples. I want to compare to the 2 samples. I'm going to be making a statement that regardless of what happens here, the difference between the two population parameters is going to be zero. So that is what I am expecting. But when I take the samples, it's very clear that my two means are different. So the observed differences, the difference in X bar 1 and X bar 2 is going to be some number, but the hypothesized difference is going to be always 0. So that's the reason we say M1 and mu1 and mu2 is going to be 0. You are going to be more clear when we look at the formula, because the way that we look at the formula, if you remember, we look at the difference between X bar and the constant in a one sample hypothesis test, and then divided by the variability of my which is measured by the standard error, right? So I do the difference between the observed and the hypothesized, and then divided by the variability of my data. So in this case, what I'm going to do is the following. So so that's what I mean. So so in this case, let me show you the standardized test is going to be the difference between the observed. So we have the sample mean for sample 1, we have the sample mean for sample 2. So this difference is going to be subtracted from the difference in the two different parameters. But in this case, the parameters are going to be 0. So all we have to do is to solve this and solve the standard error. So it's going to be very simple, as you can see. So so once we have the hypothesis, so we assume that this hypothesized difference is 0, or there is no difference. So there are 3 conditions that are necessary to perform the C-test. So remember, we have many tools in our toolbox. So one of them is the C-test. We can assume normal distribution when we have a sample that is big enough, bigger than 30 or equal than 30, or we have the value of sigma. So in this case, those are things that we need to consider. So in order to perform a 2-sample C-test for the difference between means, so there are 3 conditions that are necessary. One, the samples must be randomly selected. So remember, randomness is very important in a study. So if the samples are not random enough, they are going to provide spurious results. So results that are going to be biased. We have made this comment many times. Just imagine you are trying to determine the GPA representative of CUNY, and then you go to the honors college. Of course, everybody have a 4.0 GPA. So in this case, we can so we can assume that this is a biased sample, because that does not represent the GPAs of all the students at CUNY, right? So randomness is very important. Every time we select a sample, that sample has to be random. And we have to do extra efforts to ensure that randomness is there. So the two samples have to be independent. So make sure that those who are in group 1 are not part of group 2. So each sample must be at least 30. And if not, each population must have a normal distribution and a known standard deviation. So that means a known sigma, which is the population standard deviation. So we have gone through this several times. If I have a sample that is greater than 30, I don't care too much about sigma because I have the standard deviation of the sample. So so that can be used. But if my sample is less than 30, so I need to use so if my sample is less than 30, I need to know the standard deviation of this of the population. Okay, so those are things that we already know. So so that's the idea. So if these requirements are met, the sampling distribution for the difference between the sample means. So remember, this is the sample means of my two different samples. I am looking at the GPAs of students, male and female. So I want to collect the data. So once I find the data for let's say 30 students who are male, 30, or 30 male, 30 females. So I'm gonna take the mean of these values and then I'm gonna take the difference. So the difference of the sample means, which is the difference between sample 1 and the mean of sample 1 and the mean of sample 2. So it's gonna be represented by this element. This is the mean, the new, so the mean value of the difference of the sample means. So so in this case, we need to know the difference. And remember, every time we know the difference, we have to divide it by the degree of variability. So in this case, the standard error is going to be something very particular. So the standard error is going to be the square root of the variances of each group, right? So in this case, I need to know the variance. I need to know the variance of my first sample and the variance of the second sample. I'm gonna add them up, and then I'm gonna take the square root. If I don't have the variance, so I can, sorry, if I don't have the standard error, so I can compute the standard error by taking the variance of the first sample and divide the variance of the first group and divide this variance by the sample size. So we know how to get the standard error. So this standard error is going to be given by this formula. So so in this case, it's basically the same idea. We have a mean. We are going to find the how many standard deviations to the right, to the left. So that's what the goal of this is going to be. So so in this case, I was mentioning this a few minutes ago. So the test statistic is not going to be in this case just the sample mean. Is going to be the difference of the sample means. So this difference of the sample means are going to be subtracted from the difference of the hypothesized mean, which is the population mean. Remember, that's going to be equal to 0. So when we are computing to find the C-score, we find the difference between the samples and divided by the standard error. So once again, this is going to be the standard error. And when the samples are large, you can use the standard deviations of the samples, of the two samples, in place of the sigmas. So we don't need the sigmas when the sample is big enough. If the samples are not large, you can still use the 2-sample C-test, provided that the population are normally distributed and you know the population standard deviation. We just mentioned that before. So how do we solve this problem? That's very, very simple to do. So we are gonna do it step by step. So using a 2-sample C-test for the large difference, for the difference between means. So we have large independent samples, or we can have a small independent samples, but we know sigma. So it's the same idea. We state the two hypotheses. We identify the level of significance. Remember, the level of significance is going to be compared with the p-value. So, or in this case, we are going to transform this alpha. Sorry, this is alpha. So this alpha is going to be transformed into a z-score, and then we are going to find the critical values. So then we are going to determine the rejection. Sorry, we are going to identify alpha. We are going to identify the critical values, and then we are going to find the test statistic. So we are going to either use the rejection region or the comparison between the p-value and alpha. So in the first case, if C is in the rejection region, then we reject H naught, otherwise fail to reject. So we are going to make an interpretation of the decision in the context of the original data. So before I enter into this, so we know that we are comparing two different samples, right? So so give me 1 second. Terry asked me for this. So let me go to my email. Oh, are you, Adja, are you there? Oh, yes, you are there. Sorry, I didn't read your email. So what I was looking, Terry.
Yes, I'm here. I'm fine. Thank you.
Thank you. I just saw your email. So Terry, I'm gonna send you an email with the, I think this is the one. And please tell me if you received it. Hypothesis test, 2Samples. So please tell me if you received it. So once you open your file, so this is what you see kind of in real life. So you have data. For example, in this case, you have the Standard and Poor's. So Standard and Poor's is an indicator of the stock market. And as you can see, the units are in the 2000s, right? So, and the variation probably might not be that big. So, and we have the NASDAQ. So this is a sample of 500 enterprises in America. This is the stock market for technological firms. So some of them are trading at very high values. Some of them are using small numbers. So in this case, my point, the numbers are different. I want to know whether the mean of NASDAQ is different from the mean of the Standard Poor's, right? So if we take the mean value here, so let me do it here. So if we take the mean, we do the average, and we do the average. So as you can see, these numbers are the averages of my my values, right? So this is the average 2,600, and this is the average 7,100. So the question is, how do I know whether these two means are different from each other? So we can do the following in order to find those values. So if you have Excel already open, so you can go to, hold on. So I already did this. Let me minimize this. So there is a function in Excel. If you go to data, so there is a function in Excel that is called data analysis. I don't know if everybody can see it here, data analysis. So if you don't have it in Excel and you have a Mac, you have to go to tools and then Excel add-ins. So if you have an Excel version, if your Excel version is in Mac, go to Tools and go to Excel add-ins, and then you have to upload the analysis toolpack and the save as, well, the analysis toolpack is more than enough, right? So if you have the analysis toolpack, you're gonna see that it's gonna be there. If you don't have a Mac that I don't add ins in PCs, right? So you can do it from. So you have to follow these things, right? So I really don't know exactly what else I can advise you, but find a way to upload this data analysis. So once again, for Excel in Mac is very simple. Go to Tools, go to Excel add-ins, and then add this package. If you are using the 360 Office, I think there might be some guidelines on how to do it. It's not that difficult. I'm very sure that anybody can do it, and so you can do it. Okay, so I'm gonna do this only today. So you will have, if you cannot make it for today with the data analysis, we are gonna repeat this next class. I just want to show you that we have 2 different samples, 30 different days. I guess this is data from 30 different days. And I want to make sure that there is no significant differences between the 2 means. So in order to compute the population mean, so my H naught, that's a very good point. So my H naught is gonna be that mu of the SP is equal to the mu of NASDAQ, right? So my alternative is gonna be that the mu of the Standard & Poor's is different from my mu of NASDAQ, right? So basically I have a two-tailed test. So I'm gonna be computing a two-tailed test. So I don't know the values yet, but what I can envision here is that I'm gonna have a two-tailed test, right? So this is gonna be the rejection region, and all I need to do is to find the values, right? So this is extremely simple when you are doing this data and then data analysis. So this is super easy. So there are many things here. So we are going to be using this data analysis more often in the next couple of days. So as you can see, we have the ANOVA and some other things that we might use. The F-test and the chi-square, we also have it here. So in this case, what we need is the C-test for two samples for means, right? That's what I need to know. So I need to know whether this is these samples are equal or not equal. So of course, my claim is going to be, well, so I'm going to make this my claim because I am assuming that the two are equal. So that's what I'm claiming. So I'm saying that there is no difference between the two mu's, even though the values are different. I'm assuming that the mean value represents, so that they are equal. So I have all what I need. So in this case, I am going to assume an alpha equal to 5%, right? So how wrong I want to be? Well, just 5%. I don't want to be too wrong. I can do it at the 1% level of significance. I can do it at the 10% level of significance. In this case, just remember, people, you are dealing with money here. So a 5% might be good. In some cases, 1% or 0.1% might be also appropriate. The level of significance is something that the researcher sets depending on the type of case that you have, right? So what you want to prove. So I received it, but it's not a copy. Okay, I will send it to you, Terry, a little bit later. So so here I already have these results, these two different columns. So I am gonna use what it says here. I don't have the population mean, but I know that my sample is greater than 30. So because I have a sample that is greater than 30, I'm assuming normal distribution. So I'm gonna use not sigma, but the standard deviation of the sample. So in this case, I'm gonna use the variance. I'm gonna ask for the population variance. So, and I am gonna find group number 1. So this is the variance for my first group. So I'm gonna find the variance for my second group. So in this case, so I want to find those values because, as I said before, we need those values to compute our results. So as we can see, the variance for the Standard & Poor's is very small. However, the variance for the NASDAQ is greater. So, so in this case, what does that mean? Well, so far, it doesn't mean too much because remember, these numbers are bigger every time you find the difference, the deviations, and then square the deviations, the number is gonna be bigger and bigger and bigger. So in this case, this is not telling me anything. So we have the Standard & Poor's, we have the NASDAQ, and then we have the variances of these two. So what I'm gonna do is I'm gonna call my data, and I'm gonna call my data analysis, and I am gonna call the 2Sample for means, right? So I'm gonna say, okay. So I typed this before, I'm gonna do it again. So let me do it case by case. So, so that's a little bit of a problem with this because once you do one, you have to erase everything again to do a second case. So in this case, it's asking me for variable 1 range. So I'm gonna click here, and then I'm gonna find the beginning of my data. I can even put the labels here. So I'm gonna highlight my data. This is for the first one. I'm gonna highlight my data for the second. I'm gonna include the labels because I can tell Excel that the first one is the label, right? So remember when I said, what is the hypothesized mean difference? Well, we are expecting that the difference in the means is gonna be 0. So that is the hypothesized mean difference. We know that the mean of the 2 samples is gonna be different, but I don't care. My hypothesized mean is gonna be equal to 0. Then it's asking me for the variable 1, the variance, if I know it. So in this case, I'm gonna use 6,151.51. And for the variance 2, I'm gonna say 86,815.01, right? So I almost have everything. So in this case, my thing is I have a 2-tailed test. So in this case, I'm gonna use an alpha equal to 0.5. I'm gonna show you how you can find the data without specifying whether it's a 2-tailed test or a 1-tailed test. Here I know it's a 2-tailed test, and I'm gonna still use the 5%. I don't have to do anything different. So, so I'm gonna say I want a 5%. The output that I am gonna produce is gonna be it's gonna tell me whether it's a 1-tailed test or 2-tailed test. So I don't have to ask for anything here. So in terms of the output range, so I'm gonna ask Excel to put my values here, right? So so this is D7, and I'm gonna say okay, right? So as you can see, less than 5 seconds, I got the results. So my C value is minus 87. So that means there are 87 standard deviations to the left. So so if my so here, let me see if I can modify this number, because I need that scientific number. Probably don't have to. So this number is too close to 0, that we have a 0, 0 mean. So this 87, so just imagine that my C score, the C critical, one tail is gonna be, or for two tails, is 1.996. So I'm gonna have something, so let's use these values, and let's use just two decimals. So what this number is telling me, that my critical value for the two-tail test is gonna be here minus 1.96, and here is gonna be plus 196, right? So it's also telling me that the C value that I found is gonna be minus 87. So minus 87 means that this number, if I can elongate this line more and more and more, so minus 87 is gonna be here. So that is that number within the rejection region? Yes, it is. So that means that we are gonna reject the claim. So we are gonna, so we don't have enough evidence to support the claim that the means are equal. So in this case, this is when we are using the C scores. So this is the critical value that we found, the C critical in two tails, and this is gonna be the value that we found in our data. So we can also use the p-values. So in this case, the p-values are extremely low. So either for one tail or two tail, they are extremely low. So we can conclude that this is going to be a number that so we are going to reject H0. Okay. So so this is very simple. So as you can see, we have a one tail p-value and one tail critical value. So we have the results for the two tails, right? So we don't have to do almost anything, and the results are here, right? So this is when you have data from one side or the other, right? So, but what happens when you are just given the values as in the examples? So in our examples, so what we are gonna do is gonna be the following. So we have this example here, and I also accounted for that. So we have this, hold on, let me move this a little bit. So I did this in Excel. So we have here, so here we have group 1 and group 2. All we need to figure this out is gonna be to fill this out. So we need the sample size of group 1, sample size of group 2. We need the sample mean, I need the X bar, and I need either the sigma or the standard deviation of the sample when the sample is greater than 30 and follows a normal distribution. So let's see how we can do this. So so we have the following. So I made the note here that so we can use the variance of the population or the variance of the sample depending on what we are doing. And here this table works with the standard deviation. Okay, so that's what I wanted to say. So in this case, a credit card watchdog group claims that there is a difference in the mean credit card debt of households in New York and Texas. Of course, people who live in Texas don't live in New York. By definition, we have an independent sample. So we don't have to burn our brains to determine that this is true. So the results of a random survey of 250 households from each state are shown below. So here we have two different groups. The groups are very balanced. So we have the same number of elements in group one and in group two. It doesn't have to be the case. It cannot be the case, as we can see. So, so in this case, we have a sample size in the two households is 250 on one and 250 in the second. So as we can see, that starts finding some values. So the sample mean for one is 44, 46, 26. So we have 44, 46.25, sorry. And we have a group two with 45, 67.24, right? So as you can see, I'm finding the difference between the two groups. So that's how this formula is designed. So then those are steps in the formula. As we can see, the formula accounts for the difference in the means, in the sample means divided by the standard error. So these steps are meant to do the standard errors, okay? So, so if I put sigma here, so the whole thing is gonna be solved. So my sigma is 1045.70, and my sigma here is 1361.95, right? So you can build these formulas very, very, very easy. So you don't need to rely on what I say. You have the tools. Like for example, the way I did it is I built the numerator. So for me, it was very easy to find the numerator. I know this is 0. I don't have to account for this. I just have to account for this difference. But remember, the standard error is something that is a little bit more elaborated. So I did sigma 1 over n1, then sigma 2 over n2. So then I divided by, so I divided sigma by the two sample sizes. Then I add them up, and then I take the square root of this, right? So that is the numerator. This is the denominator. So once I have this, so I am going to compare. So I generated the C-score. So remember, the C-score here is going to be the numerator. Yeah, is the numerator over the denominator. So I'm going to divide the numerator and the denominator. So I have 1.11. So I also ask Excel to find the p-value. So this is 13%. Of course, if this is a 0.05%, so if I compare, so just by inspecting the data, if I compare the 5% alpha, so the p-value is gonna be greater than alpha, as far as I can see. So I have an alpha of 5%, and I have a p-value computed by this is 13%, right? So because p-value is greater than alpha, I am going to fail to reject. But also I can do the following. So as you can see, I'm gonna find the C-score for this. So, and I am going to do the rejection regions. So in this case, let me do that. So here we have to state the hypothesis. I forgot to do it, but so we have to state the hypothesis. We have to identify the values. So we computed this, so we have 1.14, and we determined that they, based on the critical values, so we found, so here we have the C score. So let me do this. So here I'm gonna do norm, that is that IMV probability. Because this is a two-tailed test, remember, so I'm gonna use the 0.025 probability, and my C score is gonna be 196, right? So remember this here, I am using the norm that is that this. I think sometimes different versions of Excel are, so in this case, I don't know why it's doing this, but so it's the same formula that we use. So in this case, we have the data, we are finding the test statistic, which is the C statistic, and we are finding the area under the curve. So we compare the alpha with the area under the curve, and we can make a call that we fail to reject because alpha is less than, is greater than the p-value, right? So, or the p-value is greater than alpha. So in this case, we have a 13% p-value and a 5% alpha. So also we can compare the C statistic, in this case, so we can compare this C stat with the rejection regions, right? So let's do that. So what I'm gonna do here, I'm gonna make this bigger. So in this case, what we have is the following. So we have our normal distribution, right? So I am going to use alpha as a 5%, and I don't need to do many things. Alpha is greater, is p-value greater than 5%. But now I'm gonna do this. I am gonna say this is a two-tailed test, right? So that's what we determine based on our case. So we are going to, this is the rejection from the non-rejection region. So we have on the side 1.96 on the left and plus 196 on the right? So, and my test statistic is minus 1.1. So it doesn't fall within the rejection region. Therefore, we fail to reject. So what we are gonna do is that we are gonna fail to reject, and we are gonna say at the 5% level of significance, because this is the claim and we are failing to reject, we don't have enough evidence to support the claim. We cannot say that the means are different. So at the 5% level of significance, there is not enough evidence to support the group's claim that there is a difference in the mean credit debit card of households in Texas and New York, right? So, so in this case, so that's what we that's what we determine. So remember what we did here, the alpha equal to 5%. So remember we took the 0.025. So that is the cumulative area to the left, and this is the 0.75, right? So either one that we find, if we use the 0.025, we are gonna find this. If we are using the 9.75, we are gonna find this. So whichever we find first, so we just change the number. So this is because this is a two-tailed test, okay? So so that was kind of easy. So So we took the difference between the two means. We assume that the hypothesized difference is 0, and then we solve by the standard error. So in this case, we were able to find the C-score, and then we compare the C-score with the C-score of alpha. And because this alpha is a two-tailed test, we took the 0.025 or the 0.975 to find the C-score, which is the critical value, right? So this is the C-stat. So we are gonna call this the C-critical, right? So this is gonna be my C-critical, and that should be a C. My C-critical, okay? So that's the value, which is 196, okay? So we can use this. So once again, you don't need to do many modifications. All you have to do is to fill this out and use it. So it's very easy if we use the C-scores, even though here the question is find the rejection regions. But so once again, we can do the rejection regions if we transform this area under the curve in the corresponding critical value, okay? So I hope this is clear. And let me see if we have another case. So we have a second case. Hello?
Can I see one more time the Z critical?
Sure,
formula?
of course.
Just the formula.
This one, right?
Yeah.
So this is the norm.s.imb. So I usually don't remember. So what I do is I always have my, so remember I put these directions in Blackboard. So you can refer to Blackboard every time you want to do this. So we can do a second case. I don't think we have a second case, but we can do it. So this is very simple. So what I'm gonna do is the following. I'm gonna copy. I'm gonna paste it somewhere else, right? So I'm copying and pasting the same numbers. So I'm gonna erase the inputs. So probably it probably makes sense if I say C critical, right? So that's what I'm gonna do. So this C critical is gonna be equal to the norm that did I say IMB? Yeah. So that's gonna be the probability. So every time I compute this number is gonna be here. So let me make this in gray. So that was a very good comment. So I'm gonna make it green. Not the same green, but anyways, it doesn't matter. So let's solve the second. So I don't have to be looking for something else. I have this is the alpha. So this is the alpha that is gonna provide, is gonna be compared to the p-value, right? So that is one step. The second is to compare the two critical values. So to compare the two critical values, and we can do that very easily, right? This is one, and this is the second. So so now let's see the cases that we have here. So so the case is basically a travel agency claims that the average daily cost of meals and lodging for vacationing in Texas is less than the same average cost of vacationing in Virginia. So the table shows the results of a random survey of vacationers in each state. The two samples are independent, and at 1% level of significance, is there enough evidence to support the claim? Now let's do it in the proper way. So let's state the hypothesis, right? So my H sub 0 and my H sub A, right? So we are looking for the mean value. So the mean of Texas compared to the mean of Virginia. In the two cases, mu of Texas versus the mu of Virginia. And the thing is, Texas is less than the value of Virginia. So the counter argument is going to be greater than equal to. So we are going to assume that this is my claim, right? So because, well, this is the claim. Let me enhance this a little bit more. So this is my claim, right? So I have my hypothesis, and it says that the mean cost of vacationing in Texas is cheaper than vacationing in Virginia. So my alpha here, so let me, my alpha here is going to be, so in this case, because I have a left tail test, I forgot to do that. So, so I'm going to have my left tail test. So I need to find the critical value at the 1%, right? So this area under the curve is going to be 0.01, right? So now I have all the data that all the things that I need. So the sample size here in the first group is 50. The second group is going to be 35, right? So we have the sample mean for Texas, which is 216, and the sample mean for Virginia is 222, right? So sigma, in this case, we don't have sigma, but we have a big sample size, so we can use the standard deviation of the sample for this. So this is 18, and this in this case is 24, right? So as we can see, we have the numerator, we have the denominator, and then we have the C stat. So this, if I divide the numerator by the denominator, I'm gonna have the C statistic. Now I'm gonna use the 0.01%. So, and the goal, as I mentioned before, is to test this, right? So I'm gonna use the critical values. So the C critical, let's make these numbers with just 2 decimals, too many decimals. So those are minus 0.33. So my C critical is 233. .33, which is minus. And my C stat, the number that I computed here, is going to be 1.25, right? 1.25 negative, right? So I can see that it doesn't fall in the rejection region. So it's outside of the rejection region. I'm going to fail to reject. Also, I can compare the alpha, which is the 1%, with the p-value, which is 10%. So in this case, the p-value is greater than alpha. Therefore, I fail to reject, right? So very simple, this table gives me the alpha versus the p-value or the critical values, so I can make the right call. So, so in this case, 1.25 versus 2.33, so we fail to reject. So in this case, as I said before, if you have the data, you can do it as well. So we have the C and the p-values, so we can very easily determine if we have the data versus we have the values only, okay? So I hope it helps. Is there any questions so far? Is there any questions so far? No? So I think I'm gonna continue next class. So if you don't have questions, or hold on. So No, we end at 7:30. So in the next couple of days, we are gonna be doing this testing the difference between the means when the samples are small. And this is kind of long. I recommend you guys to take a look at the slides before we do the class so we can get some familiar with this. The math involved, as we can see, it's not complicated, but it's more elaborated. So as you can see, we have these big formulas. So I want you to understand how these formulas are computed, but also computing the formulas is gonna be like a piece of cake. So, so we are gonna do this next time. So is there any question?
Yes, Professor. Can I talk to you after everybody leaves?
Absolutely, you certainly can.
All right.
You certainly can. Okay. So if there is no more question, guys, I am going to wish you a